So real quickly, last time we had 4 famous ways of finding limits. Last time we added a really nice 5th limit called the L'Hopital rule, which said if you've got the right form and this limit exists, the process becomes a million times more cleaner and elegant. And we did that for many limits. That's got to be one of the nicest uses of derivatives. And so we can put that on there and say, hey, what can we do with derivatives? Well, for instance, we can add another method to our methods for finding limits, L'Hopital. And so what we want to do today is expand on that. What else can we do with limits? And so we want to start adding more things here. By the way, these are almost all independent. And so in this chapter, the chapter is a little different than the other ones because it doesn't so much build on top of the other very much. It's much more independent. For example, you could do section 1 today, you could do section 4 the next day. You wouldn't miss a beat. There might be a couple that are related, but not that much. In any case, what we want to do today is add some more to the list. What have you done for me lately? The derivative. And so today we want to do this thing called linear approximations. And linear approximations, well, a lot of these things are just done out of the historical consequences of the limits. They're done just not so much because we need to, but because we like to. For example, here, suppose you wanted to approximate the square root of 15.95. You wanted to approximate that with no calculators. See, before, a long time ago, they didn't have these things right here. They didn't have Walmart. They didn't have the Google, the internet, nothing. People had to use their brain and their creativity, and so that's no longer the case anymore. You could just plug this in anything. The calculators are everywhere. You're probably wearing one right now if you have a phone. So they're not done so much out of necessity. You don't really need to know how to do this. You could just plug in the calculator. They're more done out of the historical context of the ideas and more of a history of ideas than a necessity. Okay, that's the case for a lot of these topics, by the way. But still, I think it's really nice to see. We will be able to approximate this with no calculators, nothing. Just paper and pencil, noodle power, and pride. And then you could extend that to other things. The square root of 81, you could do cubic roots. There's a lot of functions that you could approximate using the ideas of derivatives with nothing but a little pride and some free time. So in order to do this, we're going to need some key ingredients. So I thought I could write them down. The key ingredients that we need is we need to become super good at finding the equation of a line and knowing what is required to find the equation of a line. We will need to know not just any line. We will need to know the equation of the tangent line. And of course, we need to study similarity between the function and the linear approximation of the function at that point. Once we've got these 3 ingredients, we will be able to do this with great ease and a little bit of elegance. Okay, so let's get to it. The first thing we got to do is figure out how do you write the equation of the line. This isn't so much, there's not much calculus in this. This is more a review of your algebra class. Okay? So suppose somebody gives you these 2 ingredients. They give you m, which is the slope, and they give you a point, 47. That should be enough for you to find the equation of the line. And again, this should be a review from a long time ago. Here's how it goes. You go like this. You go y minus 7, and that's equal to the slope, which would be 2 times x minus 4. There it is. That's again, I'm not going into the details. This should be a review from a long time ago. This is the equation of the line that has slope 2, and it goes through the point 47. And of course, sometimes you could write the y over there. You could just go like this: 2x minus 4 plus 7. And of course, for our purposes, we won't just call it a y. We will actually give it a name. We'll call it a function. P of x is equal to 2 times x minus 4 plus 7. That's the way we will do it. Okay. That part is, again, it's just review. Maybe we could try it a couple more times. Suppose you had an equation that has slope negative 2/3 and it goes through the point 1,3. How would you write the equation? Well, you could do it in one stroke. Go like this: y minus 3, y minus the y-axis is equal to the y-coordinate, negative 2/3 times x minus 1. And you're pretty much done. You can move this to the other side, of course. Y is equal to 3 plus a negative 2/3 times x minus 1. And that's okay. And again, we will use a p of x, meaning a polynomial approximation of the function of degree 1. This has some implications for future lessons, so that's why I'm calling it p of x. If you're tempted to call it something else, I would suggest you stick with the program here. Let's call it p of x, because it'll make things easier, a little bit easier. Who cares about the name anyways? But it has implications for future lessons when we do a polynomial or other approximations of functions. Anyways, that's how you write the equation of the line. Pretty basic, right? You could clean this up if you wanted to, but I'm not that interested in that. The slope could be all sorts of things, and the point could be all sorts of crazy things. For example, the slope could be pi, and that shouldn't scare you or make the process any different. You'd go y minus 3 is equal to the slope times x minus x coordinate, but this is minus 1, so it makes it a plus 1. That becomes y is equal to 3 plus pi times x plus 1, or said differently, our function here is 3 plus pi times x plus 1. See that? It's way too easy. Yeah, this is just review. Again, this could be any sort of crazy thing, and this could be any sort of thing, and this could be any sort of crazy thing, and you shouldn't not have a problem with it. You'd go like this: y minus this diamond is equal to the star times x minus the square, whatever's in there. It should be automatic. Maybe we do one last one. Of course, the most important one. What happens when the slope is f prime of c and the point is c comma fc? Well, when that happens, you get y minus f of c is equal to f prime of c times excuse me, times x minus c. So that becomes y is equal to f of c plus f prime of c times x minus c. Of course, we can change that into a function notation. F of c plus f prime of c times x minus c. This is incredibly important. I may, for the rest of the lecture today, skip all these steps and just get to the real one, the most, of course, important one. And if I write this, you shouldn't sit there wondering, where did that come from? It comes from just basic things from algebra, writing the equation of the line. When you know your two ingredients, the slope and the point of the line. Capiche? Alright, so again, we needed the equation of a line. You know that you need m and you need a point. Okay, check. Equation of the tangent line. Well, that's almost checked. That's going to be exactly this, because for any curve here, if you have a point here, the equation of the tangent line, the derivative would be this, and the point would be c, and the y would be f of c. So of course, this is the equation of the tangent line at the point c, assuming such a thing exists. That's that. Now let me explain about the similarity business. And we'll do this one as well. So here's the similarity business. Suppose that at 16, suppose I go for the point 16. Okay, at 16, when the function is equal to the square root of x, if I plug in 16 here, I get that the y value is 4. And I could make a, let me make a tangent line here at 16. Well, it's not bad. Yeah. There it is, a tangent line at 16. It goes through this point right here. And so, suppose you wanted to find the equation for that line. That line right there, that's the line we will call p of x. And this is the line f of x, which is equal to the square root of x. Now, so here's the thing. Around here, around this little neighborhood, that means for numbers that are really, really close to 16 on either side, around here, the p of x, the polynomial that we find, the line, and the f of x are almost the same. They're very, very similar. They're almost indistinguishable. The closer you get to 16, the more approximately equal that these become. That's going to be the key right there, because here's the key. Because they are so similar near that point, if I wanted to find the square root of 15.95, I wouldn't plug it into there. I would plug it into the equation, and because they're similar, into the line, and I'll get an approximately good answer. That's the key right there. And the fact that this is a square root, this is difficult to evaluate. Well, just pretend it's difficult to evaluate, okay? But back then it was difficult. This one is incredibly easy to evaluate. We're going to be in good shape. We're going to be able to do this with no calculators, just noodle power. Okay? Alright, talk is cheap. Let's actually do it. Can you guys tell me, can you think about, you can't tell me anything. Can you think about f prime of x? So if f of x is equal to x to the 1/2, which is the square root of x, how do you take the derivative of it? You bring that down, and then you subtract 1 from there. Whoa, can you see that? Sorry. There you go. That becomes 1 over 2 times the square root of x. So f prime at 16 would be equal to 1 over 2 times the square root of 16. I reckon that's 1 over 2 times 4. That's 1 over 8. F prime of 16 is 1 over 8. So here, my friends, I've got my slope here. For this line, m is equal to 1 over 8. And I've got a point on there. The point is 16, 4. I've got my two key ingredients. The two key ingredients. Okay? The two key ingredients are the slope and the point on the line. Now, I need another new clean page, so let's clone this, and then let's clear this page. So now I've got this. So I've got. I'll just do it ghetto style here. I got that the slope is equal to 1 over 8, and I've got that the point is equal to 16, 4. So therefore, my function y minus 4, I said I wasn't going to do this anymore, but I'll do it one more time. 1 over 8 x minus 16, so that becomes that y is equal to 4 plus 1 over 8 times x minus 1 over 16. That's my p of x. My polynomial is equal to 4 plus 1 over 8 times x minus 16. That, my friends, that's nice, because now I want p of 15.95. That's easy to do. That's 4 plus 1 over 8. So instead of evaluating it here, here's 16. This is 15.95. The function is really, really difficult, but the line is easier. So I'm going to evaluate the line at 15.95. That's, what is that? 15 and 15.95 minus 16. This I can do by hand because I could easily turn this into a fraction. This is 5 over 100. This would be 4 plus 1 over 8 times negative 5 over 100. And that becomes negative 1/20th. So that becomes 4. I continue over here. 4 plus 1/8 times negative 1 over 20. That becomes 4 minus 1 over 160. And that becomes 6 por 4, 24, 40, 64, and then another 0. Over 160 minus 1 over 160, that becomes 639 over 160. Yippee-ki-yay. There you go, my friends. Think about what we did. I just wrote that the square root of 15.95 is approximately equal to 639 all over 160. Just like that. Did I use a calculator? No. It's the little pride and noodle power. And I use these crucial ideas here. The fact that at 15.9 the line is almost the same as the actual function, but the function is difficult. F of 15.95, that's troublesome. You got to do square roots. But this one is much easier. This is just a line. All I did is plug it into the line, and there you go. And it's also interesting. You might want to check to see how far off we were on that approximation. Let me see if we can do it. I don't know if we've got the tools. Yeah, I'll let you guys try that. Check this and see how close we were to it. But I suspect we were really close, because 15.95 is really close to 16. The closer you get, the closer that the line is to the actual function. Okay, that was fun, right? I'll try it again. This time I want to approximate the square root of 81.25. So what I want to do is I want to go to a different point, 81. Because at that point I got a perfect square. F of 81 is equal to the square root of 81, which is equal to 9. See, I wouldn't pick 87 or something crazy like that, because I can't find the square root. So I'm gonna be back to not being able to compute it. I want to use numbers that I can't compute without a calculator. 81 seems to do the trick here. 81.9. I've already got one of my key ingredients here. 81.9. The other key ingredient, f prime of x, I had calculated before, was 1 over 2 square root of x. You plug 81 in there, you get 1 over 18. Check. The slope is 1 over 18. That's the slope for my tangent line. I got my two ingredients. Whoa, it's not that tangent, huh? There's kind of tangent. I've got my two ingredients, my slope and the line, and I know that. Again, let me try to emphasize this part right here. My best linear approximation, that's that one right there, P of x is the line, is equal to f of 81 plus f prime of 81 times x minus 81. Right? Can you see that or not? If you can't see it, too bad. I'm just kidding. I can move it over here. Except the arrows don't match. But whatever. That's my polynomial. F of 81 plus f prime of 81. I've got all of them. Here's my f prime. Here's my 81 is a 9. And so you get that the equation is P of x is equal to f of 81. That's 9. Plus the slope, 1 over 18 times x minus 81. There you go. We find the equation of the tangent line. This is called the equation of the tangent line. And now, if I wanted it to approximate square root of 81, all I do is take my equation of the tangent line. Let's see if we can do this. Take this one and then copy it. Take this one over here, paste it, and all I do is plug in 81 there. Because this guy is approximately equal to the polynomial, or to the line evaluated there. This is f of 81.25, but it's almost equal to p of 81.25. So all I do is take my 81.5 and plug it in here, so I would get p of 81.25 is equal to 9 plus 1/18 times 81.25 minus 81, and then you clean it up. 9 plus 1 over 18 times 81 1/4. Take away 81. I reckon that's just a quarter. So that gives you 9 plus 1 over 40, 72. Is that right? And that becomes, let me see, 630 plus 18, 648 over 72 plus 1 over 72. Can you see that or not? Aha. And then that becomes, let me think, what does that become? I reckon that becomes 649 all over 72. Really nice. This guy here, square root of 81 over 25, approximately that. With no calculators. No, we don't need this. No soul, no blood running through it, no pulse. I'm checking. It's got no pulse. Human creativity. Nice, huh? Completely useless, by the way, because you could just use the Google or the calculator. But a really nice idea. Using the linear approximation to evaluate functions. Want to do it one more time? Let's do it last time. Let's do it one last time. Let's do the cubic root of 123.5 with nothing but noodle power and a little bit of pride. Why? Not because you need to. No, you don't need to. Just for fun. Okay? Why do people climb Mount Everest? Do they need to? No. It's because humans love a challenge. And also because it's part of the course outline. Yeah. We have to do this. It's more for historical reasons, I'm telling you. It's not really for necessity. We don't really need to do it. Anyways, what we got to do here is, let's see, let's set it up here. F of x is equal to the cubic root of x. What we're being asked to contemplate is to evaluate that at 123. Oh man, I'm getting old. 123, that's what we have to do, evaluate it. And you say, well, that's too hard, man. I can't do that. If it was 125, I could do it. 125 I can handle because I know the cubic root of 125 is, of course, 5. That I could handle. This one is a little bit hard. Let's say, I know. I'll go here, 125, and then I'll try to reason. I'll draw a tangent line to here, and then I'll find the equation of that tangent line, and then I'll use the line. I'll plug this back into the line because they're almost the same at that point, and then we'll be good. You see the reasoning? It's flawless. Very nice reasoning. It's a good way to approximate it. So then you think, okay, I want to get this line. I need two ingredients for the line. I need a slope and a point. I've already got a point. 125, 5. I need a slope. Well, for the slope, I wish I had a good way to find tangent slopes. Oh, wait a minute. We just did 2 chapters on derivatives. We know how to find slopes. For that guy right there, f of x is equal to x to the 1/3. F prime of x is equal to 1/3 x to the negative 2/3. Or f prime of x is equal to 1/3 cubic root of x quantity squared. I want to find that at 125. So that would be 3 times the cubic root of 125 squared. I reckon that's 1/3. Cubic root of 125 is 5. 5 squared is 25. I reckon that's 1/75. Oh, hey, you know what's nice about this? You can tell me, oh, wait, you went too fast. You could just pause it. That's right. All right. So I've got my 2. Of course, the bad thing is I probably made a mistake. Let me check that. Make sure I didn't make a mistake. I'm the king of mistakes. 5. Yeah, that's 525. Yeah, it looks good. So much for saving time. 1/75. Is that right? 1/75. So I got my 2 key ingredients. So therefore my slope is equal to 5 plus 1/75 times x minus 125. Just like that. And now I evaluate that at 123.5. Polynomial of 123.5. That's equal to 5 plus 1/75 times 123.5 minus 125. This is actually easy to compute. You got 123.5 minus 125. I think we need more room there. More? Yeah. That becomes 5 plus 1/75 times negative 3/2. That's negative 1.5. That becomes 5 plus negative 3/150. That becomes 5 times 150. How much is that? 750 over 150 minus 3/150. Is that right? Are you running out of room again? Let's extend this. You got that? That becomes, let me think. 750 take away 3. 747 all over 150. That, my friends, that is approximately the cubic root of 123.5, approximately, using nothing but noodle power. Pretty nice, huh? It's a nice little note to end on.